Hi, everyone. Thank you for coming to this virtual talk. I know the conditions are not the best right now, so I appreciate anyone taking the time to watch this. So today, I'd like to share with you a recent result of myself, Jan Vondrak, and Wenjin Lee from Stanford University on the adaptive complexity of submodular optimization. So this talk, like the paper, will be broken into two parts, and you can find the slides and the paper in the description below. I'll begin with a bit of background material, so apologies if this is familiar to people, but luckily this is on YouTube, so you can just fast forward a few minutes. The rest of us will pass time in the normal way, and we'll see you in a few slides. Okay, so to begin with, perhaps a familiar setup that many of us have seen is the setting of combinatorial optimization, where you have a function f defined on subsets of a set of objects. Now, one general framework for such functions is the setting of submodular optimization, which generalizes classic problems like min and max cut, maximum coverage, and so on. So a function is submodular when you have the so-called diminishing returns property, which I've just underlined. And it's basically the property that as you add more elements to the set, the gain from adding the element decreases. In addition, we're going to be looking at monotone submodular functions in the first part. And a function is monotone if adding more elements to the set only increases the value. So this is not the case for max cut, for example, since adding every node to the cut set makes the cut 0 and the empty set also has value 0, and in between it's higher. In this talk, we'll mostly be concerned with maximizing the submodular functions. I know Eric also has another talk about minimization, so I hope you'll go to that talk as well. In addition to this, we'll be constraining our maximization problem with a cardinality constraint. So we're only going to be optimizing over sets of size k or less. An example you can keep in your head is the coverage function, which I've illustrated on the right here. And in this example, you're given a set of geometric shapes, such as circles, and the subsets you're selecting over is the shapes themselves, and the value of the function with that set of shapes is the union of the area covered by the shapes. So if we were maximizing the function with a cardinality constraint of size 2, we'd find the pair of circles in the input that has maximum area. So the problem of submodular optimization is actually well studied, and you might have encountered the classic greedy algorithm where you take elements one by one, maximizing the gain. In our setting of constrained cardinality submodular optimization, this algorithm actually obtains an approximation ratio of 1 minus 1 over e. And this ratio is actually optimal if you're only allowed to query the function f a polynomial number of times. Okay, but nowadays people are highly interested in the parallel computational regime, and the classic greedy algorithm is actually pretty terrible in this regime. If you think about the greedy algorithm, each additional element is computed based on the current set you have gathered so far. So when you run the algorithm, this causes quite a long chain of sequentially dependent queries. So one question asked by Balkansky et al. Is whether we can make the greedy algorithm parallel. And the answer is actually yes. So they formalize a model called the adaptive complexity model. And in their model, they define rounds of queries where all the queries are independent. And the computational cost of an algorithm is then the length of the longest sequentially dependent chain. So in this model, the greedy algorithm is actually an O of k cost algorithm. And a result of them in 2018 by Balkansky, Rubinstein, and Singer shows that you can get close to 1 minus 1 over e, And you can do this in 1 over epsilon squared log n rounds of parallel queries. In another paper by Bolkansky and Singer in 2018, they also showed that you cannot even get a constant factor approximation without log n over log n rounds. So the question we're interested in for this paper is whether the number of rounds must blow up as we approach the factor of 1 minus 1 over e. And we show that yes, we do have to blow up the number of rounds as we approach 1 minus 1 over e. And in fact, we have two different regimes. One for when the number of rounds is at most log, and the other for when the number of rounds is some polynomial, n to the c for some c less than 1. The reason for the two different regimes is technical and relates to an optimization problem we solve while proving the lower bound, which we'll talk a bit about later. The main ingredients in the proof, there's actually 3 main ingredients in the proof, and the first is the onion layer construction inspired by Bolkansky and Singer's 2018 paper. The second is the symmetry gap construction from Yan in 2009. And the final ingredient is an improved 1 minus 1 over e hardness instance that we'll use as the core of our onion. So our hardness function f is constructed from our layers x1 to xr and a core layer x star, sort of like an onion. And this onion has layers that are decreasing geometrically in size or slower, depending on whether we are in the log regime or the poly round regime from the previous slide. So you can imagine x2 as being either about half of x1 or maybe roughly equal to x1 size. Okay. And then in the ith round, we'll make sure no polynomial number of queries on F can determine the layers from I plus 2 to R as well as X star. However, given the ith layer, we only need polynomially many queries to determine Xi plus 1. So this way the algorithm keeps making progress towards the end. Now in the final layer X star, we'll embed a 1 minus 1 over e hardness instance, which will stop any algorithm from progressing beyond the 1 minus 1 over e approximation factor. Let's describe f in more detail. For any query s, let xi be basically the intersection size of s and xi normalized. And the reason we normalize it this way is so that when you query a set S of a size exactly k, the sum of the xi values sum up to 1 for the optimal solution. Oh, and also we'll define a little x star to be the intersection of S and x star appropriately normalized. Furthermore, we let x0 equals 0. So the function f is written below. Let's try to make sense of it piece by piece. First of all, the function itself is a product of several different functions, and each function only operates on either one layer or two adjacent layers. Now, because x0 equals 0, the first term in the product here is actually 1 minus h of 0, x1. And this is what allows the first layer to be determined by an algorithm. Now, we'll construct this function h so that unless you're given the layer xk or the layer xk plus 1, you cannot deduce anything about either of the layers. Finally, the function g will encode a 1 minus 1 over e plus low O1 hard instance. So we'll not describe how to construct the function g here, and more details about that can be found in the paper. But we will talk about the function h. So when all the layers are revealed, you can actually get each of the h's to be approximately 0 in value. So that means when all the layers are revealed, f will be approximately g, and 1 minus 1 over e is the best we can do. So what does h actually look like? Well, roughly it's close to 1 minus half of e to the negative x plus e to the negative y. And it's largest when x is equal to y and sort of decreases as x gets further away from y. When the query between two layers, xi and xi plus 1, are approximately equal, h of xi plus 1 will be approximately 1 minus the exponential of the sum of the xi's. And the reason this is important is if we go back to the previous slide, this function h here will be about 1 minus e to the exponential of negative xi minus xi plus 1, and these 1's will cancel out, leaving just positive e to the negative xi plus 1. Now, the product of all those xi's together will be the sum of twice e to the negative xi. Oh, sorry, I see my face is in the corner here, so let me remove myself. And because all of the xi layers are summed, none of the xi's can be distinguished. Now, why do we care about the edge case where the xi's are approximately equal to the xi plus 1's? That's because for a random set S, when all the sets xi are about equal size, the random set S equally partitions into each set. So we're actually very frequently in this regime where the xi and xi plus 1's are equal. If we choose the sets x1 to xr and x star totally at random, then no matter what query the algorithm issues, it'll be roughly equally partitioned among the sets, unless the algorithm knows the elements in the layers themselves. So for all the layers that the algorithm doesn't know, we get this equal partitioning, and then we get the case where h of xi plus 1 is 1 minus e to the sum, which gets us this indistinguishability property over here. Now, when x and y are further apart, there's actually a penalty term that's roughly quadratic. Each of the h's contribute one such term, so the total penalty is approximately the sum of the differences of the xi's. And this penalty term is non-zero for two reasons. First, because x0 is 0, and because xi's sum up to 1. So this causes a gap between x0 and x1, which makes the algorithm start below 1 minus 1 over e in the first round. So once you discover a layer, you can manipulate its value of xi as you wish. And if you solve this optimization problem, you'll find that as you discover more and more layers, the penalty actually scales like 1 over k cubed, where k is the number of layers discovered. And this is what makes the algorithm approach 1 minus 1 over e at a consistent rate as more layers are found. Now, for the case where there are most log rounds, this penalty expression actually changes. So this penalty expression that I wrote here is for equal size layers. And for non-equal size layers, say the layer is decreasing by factors of 2, there's actually a 2 here in front, which changes the optimal assignment of the variables. And when there's a 2 out in front, we actually get a theta 1 over k penalty term. So it's considerably larger and gives us a better bound in that case. With this function, the best approximation we can get in k rounds is actually 1 minus 1 over e plus a little of 1 from the hardness instance g, and then subtracted by the penalty term we found earlier. So for the whole thing to approach 1 minus 1 over e from below, the little 1 needs to be smaller than 1 over k cubed, where k is at most the number of rounds. So in the regime where the number of rounds is actually polynomial in n, that is n to the some constant less than 1, we actually need the little o of 1 term to be inverse polynomial in n. But the best previously known instances, for example, in Bondrak 2009, only has a 1 over log n factor as the little o of 1. In this paper, we also found a new hardness instance that has the required 1 over poly n little o of 1 factor using similar techniques from Yan's paper in 2013. That sums up the lower bound for the constrained monotone case. Now let's switch gears for a bit and talk about the unconstrained non-monotone case. So in this case, we're considering f as a submodular function, but it is non-monotone, which means as we add elements to our set, the value of f may actually decrease. One example, as mentioned before, is if you have a cut problem, the size of the cut starts from 0 if you have the empty set, and ends with 0 if you have the set of all vertices, and in between it could be higher. So furthermore, we're in the setting where there's no constraint on the number of elements in our optimal set. And one known result in this setting is that a random set R already gets about 1/4 of the optimal. And the best result possible is a 1/2 approximation, which you can get via the classical double greedy algorithm by Bookbinder, Feldman, Ior, and Schwartz in 2012. And it turns out this 1/2 approximation is actually optimal in that no algorithm can get better than 1/2 in a polynomial number of queries. Now in the adaptive model, 2 independent works in 2018 were able to show that you can get 1/2 minus epsilon in 1 over epsilon rounds. And this is done through a variant of the double greedy algorithm, where the optimization is done on a continuous proxy for f called the multilinear extension. So these 2 results are by Chen, Feldman, Carbasi, and also Ine, Nguyen, and Vladu. One might think that maybe we can adapt our techniques to produce a hardness instance for the non-monotone case. So let's think about our hardness result for the monotone case and see what properties it has. It starts greater than epsilon times opt away. Let's assume epsilon is some small constant. And no matter how many rounds we use, it never exceeds 1 minus 1 over e plus little of 1, where the little of 1 is about 1 over poly n large. And it's also independent of the constant epsilon, since this is the hardness instance we embed in G. So even after all its rounds were complete, it could not achieve more than 1 minus 1 over e. And one might ask if there are similar hardness results in the unconstrained case where you start sort of far away from 1/2 and then can't get beyond 1/2. And surprisingly, the answer is no. So we show that the performance of the double greedy algorithm is actually dependent on how far you are away from 1/2 in the first place. In fact, the performance is dependent on how far a uniformly random subset is from half the optimal solution. We show that the closer the random set is to 1/2, the slower the double greedy takes to get to the optimal solution. So if the random set is about 1/2 minus delta away, then we can get above 1/2. We get 1/2 plus delta squared in 1 over delta squared rounds. So either we're already close to opt over 2, or the double greedy solution finds something significantly better. This is in contrast to the monotone case, where our solution can start relatively far and still never exceed. what's the intuition for this result? Well, in the adaptive double greedy algorithm, we basically do a bidirectional type of gradient descent on the multilinear extension. So x moves in the positive direction, the positive coordinates of the gradient, and y moves in the negative coordinates of the gradient, and they start at 0 and 1 respectively. And this algorithm continues until the 2 points meet. So in the hardness instances by Yan and Murakni and Phage in 2007, if you run double greedy on those instances, they actually get right to the 1/2 point. So intuitively, the hardest instances for this non-monotone case are actually the easiest ones in the adaptive model because you can just return the random set. So a key lemma in the analysis of the adaptive continuous double greedy is that the double greedy actually gets a little bit more than 1/2. It gets a little bit more than 1/2 by this factor here that's proportional to the L2 norm of the gradients at x and y. So actually in our analysis, our key lemma is to show that if you relate the double greedy solution with the value of a uniform subset, you get a similar expression. Because the similar factor appears, and since the top is squared and the bottom is not, we can apply Cauchy-Schwarz to get our desired result. And this is what gives the squared factor in the 1 over delta round result here. Okay, so that about wraps up the non-monotone case. So I'd like to end with some open problems relating to our paper, most of which are somewhat technical in nature, but still fun to think about. The first one is whether there exists a lower bound for non-monotone optimization. So as we observed, we can't have similar types of lower bounds in the monotone case as the non-monotone case. But this doesn't really prevent lower bounds where the function can actually go beyond 1/2, and it just takes a large number of rounds to get there. The second question that we're wondering about is also pertaining to the non-monotone case. It seems like if we're delta away from 1/2 in the random set, 1 over delta rounds should be enough to get to 1/2. But because of this Cauchy-Schwarz that we're applying in the analysis, we have this 1 over delta squared factor instead. And we currently don't know how to get around this. And the last question also relates to the monotone case. So we had these two different cases for whether it was poly round or log round due to the form of the penalty term that we were optimizing. And this also seems like it's something that's quite artificial in the analysis. So it seems like there should be some construction that always gets the superior log round guarantee. So that's all for the talk. Thanks so much again to everybody who stuck around until the end of the video. And I hope to see some of you at the question session at Stock 2020.